We are Team ME31, and our project is a protein-based photovoltaic electrochemical cell. Our sponsor is Lambda Vision, and our faculty advisor is Dr. Ur Pasauyari.
Polymer electrolyte membrane, or PEM, cells are an energy technology which focuses on the use of electricity to produce hydrogen gas via water splitting. One variant of a PEM cell is a photovoltaic electrochemical cell, or PVEC, which is solar powered, becoming a completely clean and renewable source of hydrogen gas. In a typical PEM cell, water and electricity are put into the system, while hydrogen and oxygen gases are produced through a sequence of two half reactions, as shown at the bottom of the slide. These half reactions are known as the oxygen evolution reaction, or OER, at the anode, and hydrogen evolution reaction, or HER, at the cathode. These half reactions are driven by an overall theoretical cell potential of 1.23 volts. However, in a real cell, there are overpotentials associated with physical properties such as activation, ohmic, and diffusion overpotentials, resulting in a more practical cell potential of approximately 1.4 volts. Bacteriorhodopsin, or BR, is a light-activated protein found in the purple membrane of Halobacterium salinarium. Due to its native salt marsh habitat, BR is characterized by high levels of thermal, chemical, and photochemical stability. As such, BR is capable of withstanding temperatures up to 80 degrees Celsius and salt concentrations roughly 5 times that of seawater. Additionally, when exposed to sunlight, a photocycle is initiated during which BR translocates a proton across the cell membrane of the archaebacteria. Lambda Vision has developed a method for layering BR onto ion-permeable scaffolds, allowing them to create BR thin films ranging from 10 to 400 layers of protein, as shown in the bottom right. These films were created such that the orientation of the BR layers forms a unidirectional proton gradient, as represented in the picture on the top right, which correlates to a high photoelectric conversion efficiency.
The goal of this project was to determine the BR thin film's capabilities to power and/or improve the performance of a PVEC. The validation of such a cell would have exciting implications on energy production and storage technology, as it would offer a more efficient way of producing hydrogen, a clean and highly energy-dense fuel. The critical path to achieve this goal was first to design and fabricate a test article based on our research and the schematics provided by Lambda Vision, as shown on the top left. The testing then began by measuring the absorbance and transmittance spectra of BR thin films with varying layer quantities. Next, we measured the open circuit voltage of two different cell designs under 100 watts of illumination to quantify the photovoltaic response that various films could contribute to the required overall cell potential. The short circuit current was also measured using the same testing setup, shown on the bottom left, to determine if the BR was capable of generating a photocurrent without an external power supply. At various points during testing, microscopic imaging was also conducted to track the wear of the films over time. The results of these tests informed the final cell configuration, namely the BR layer quantity, test article casing design, electrode and catalyst materials. Finally, the performance of the final cell design was evaluated by measuring the cell's current density at different input voltages with and without the presence of the light-activated BR to determine if the BR would indeed improve the cell efficiency.
Photovoltaic testing allowed selection of an appropriate BR operational characterization cell based on its ability to collect consistent and optimal results. The BR multilayer quantity selected was 50 layers due to the photovoltaic response shown in the plot to the right being the highest and the film's ability to sustain mechanical wear. Also shown in the graph is the maximum voltage produced by the cell, a value that does not exceed the voltage requirement to facilitate electrolysis, concluding that BR alone cannot drive the operation of the cell, but could present the opportunity to reduce the activation energy necessary for water splitting. Based on the results of photocurrent testing, no sustained photocurrent was observed, suggesting the necessity of an OER catalyst for electrolysis.
The results of protein testing informed the development of our full cell configuration. The cell pictured on the right incorporated a Nafion membrane in between the BR film and the platinum black carbon cloth GDE to reduce shorting risk while allowing protons to cross to the cathode. An OER catalyst was fabricated through spray deposition of platinum onto a mesh substrate shown below. Testing is currently being conducted comparing our control cell and our full cell through application of variable voltage and measurement of IV curves. A sample IV curve is shown on the slide. Curves obtained will be compared to evaluate if the protein has capability to reduce ohmic, activation, and diffusion overpotentials, contributing to cell voltage requirement. The team recommends further testing to measure photocurrent density as a function of time generated under constant voltage exposure and to measure and contain hydrogen produced by the cell. We would like to thank both our sponsor, Lambda Vision, and our faculty advisor, Dr. Pasagilari, for their assistance with this project. Thank you.